Hey gang, and welcome to the Worksheet Solutions Walkthrough for Newman Projection State of Mind. Okay, so we're plunging through alkanes, and you've been doing naming, you've been systematic and common, but now we're starting to get into looking at structures' internal energy, right? How, based on different conformations, what is the structure higher energy, lower energy? So if you've looked at the Newman projection video and maybe you've taken a gander at the worksheet, well, now we're you're here. So we're going to look at that worksheet and I'm going to give you the explanations you might be looking for. So let's do it. Okay, gang, so in problem one, we have three little sub-problems, and all we're doing is, given this Newman projection, I'm just asking to see what this structure is in bond line. So no, thinking critically about the molecule's energy just yet. So what I like to do, and remember, the dot carbon is the front carbon, this bigger circle is the back carbon. So what I like to do is actually just draw those two. So what I like to do is I have my dot carbon, and then I'll draw a line, because again, right, we're going to bond line, so just on flat paper. And then if you want to, you can kind of circle this one. So this is, the dot carbon is this carbon, and the circle carbon is this one that I'm circling right there. And then all you need to do is just fill in the groups off of it. So on this front carbon, we have two hydrogens, and then we have this isopropyl group, so one there and there. And then on the back carbon, we have a hydrogen, we have a methyl, and then a T-butyl group. So here's the methyl group, and then here is the T-butyl group. So I don't think it's that crazy, and if I want me to fill in the hydrogen, I can right there, but it's implied. So this is just to make sure you're comfortable and you actually know what's going on with the Newman projection. You know what's attached where, and then how do you go from Newman to bond line. So same process here. Let's go ahead and do a dotted carbon, and then we have a circle carbon in the back. So on the front carbon, we have a chlorine and an isopropyl group. So I'll go ahead and draw that. We have the Cl, and then we have the isopropyl group. And again, I have the hydrogen on the front, but I'm not going to draw it. And then on the back, I have a methyl and an ethyl along with a hydrogen. So we have the ethyl, the methyl, and then the H is there. Now on to the third one. Same process. And again, you don't have to, if you're doing this, that's totally fine. Doesn't matter. I'm just happen to go down to up. So on the front, we have this isopropyl group. And again, these Newman projections right there staggered, and this one's Eclipse. But for what we're trying to do in this problem, it doesn't matter. I just wanted to give you a different look. And just two hydrogens, so the front is done, and on the back we have an ethyl, and a bromine. So ethyl, and it doesn't really matter how I draw it, but it's kind of ugly. Bromine right there. So nothing super complicated. Again, just an easy problem to just step into the worksheet and make sure we know the conventions as far as the dot being the front carbon, the circle being the back carbon, and you can recognize this is attached to the back, this is attached to the front, and all of that jazz. On to problem two. Okay, gang, so in problem two, we are given a bond line structure, and then we are given, a challenge. Draw the highest energy conformation or the lowest energy conformation, or some instruction as to what Newman projection or Newman projections we should draw. So if we look at the first problem in problem two, we need to draw the highest energy conformation. So, and I do say Eclipse, right? Because to be the highest energy conformation, we need the most unstable eclipsed conformation. So if we take a look here, we want to eclipse the two biggest, bulkiest groups. We want to maximize those, high destabilizing interactions. We want as much strain as possible, steric, torsional, you name it. Okay, so we can always start with our home base. And our home base is always a dot and a circle. So just by even drawing that, we've already taken care of these two carbons. Now it's totally up to you as far as which one you want to make which. However, I think it makes sense, left to right. This can be our dot carbon, this can be our circle carbon. It's up to you. That's how I'm going to do it. That's how the solutions I've provided are, but by no means was that something you had to do. So, because we need these to be eclipsed, what I'm going to do is I'm going to draw, and I'll match it up just like I did in my solutions. I will draw my isopropyl group on this front carbon going up, And since there are no other substituents, there's just hydrogens. And remember, you're going to have your bond angles look like this. Now, remember, we need to eclipse our biggest, bulkiest group. So the isopropyl group on the front needs to be eclipsed with the T-butyl group on the back carbon. So just in the back, I'm going to go ahead. Remember, you stagger them just a smidgy. And yes, smidgy is a scientific word. So they should, they would be like on top of each other, but because we draw stuff and we need to see, right, I have the isopropyl group and the T-butyl group basically, in a line like this, okay? Sorry, my hands were not very, they were a little awkward. And just to round this off, we have a methyl group. So it doesn't matter, there's nothing else in the front that this methyl group should be eclipsed with to make it the most unstable. But I can fill in the methyl group right here. I'll even do a CH3 right there. And then we have an H left over. And you can draw, you don't have to put the CH3 there, but to be very specific, you can. All right, so this is certainly the highest energy conformation. Now, moving on to the second problem. So let me go ahead, right off the bat, get my home base started. And I will say that this is my dot and this is my circle. So we need the lowest energy conformation. So this will be anti. So remember, anti means you have your biggest group and your two biggest groups on the front and back carbons. One is down and the other is up. So fun little move right there. So what are those groups? So on the front carbon, it's the isopropyl. It's branched, right? And on the back, it's the bromine. Bromine is so much larger than two teeny little methyl groups. So I'll again do it like I have in my solutions. So on the front carbon, I'll put my isopropyl group going up, and then it won't really matter where my methyl group on the front is because it's going to, there are two methyl groups. These two groups on the back are the same, so it doesn't matter. And I'll even explicitly write CH3, and I have an H that I have not drawn on the front. Now remember, because this needs to be lowest energy, and that means since we're looking for anti, we need to have our biggest group on the back completely opposite of the biggest group on the front. So bromine, by definition, we need to be staggered, and the bromine needs to be completely opposite of the isopropyl group. Yes, when you're taking your test and you need to, draw an anti-Newman projection, you have to, by law, this or this. And then fill in your methyl group. So a CH3 will go here, and a CH3 will go there. So this is the lowest energy Newman projection, conformation. Now here's kind of like me going into like using acid-base terminology, trying to make things confusing, but I know you can decipher it. We need the most stable eclipse. So we need the most stable, unstable version. We need the unstable version that's the most stable. So again, remember, we can go ahead and this is our dot, this is our circle, dot. So we need everything to be eclipsed, but we don't want our biggest groups to be in a line with each other. So the two biggest groups on the front, we do have this measly ethyl group, but that's all we have. And on the back, we have this group with an iodine, and iodine is huge. So we do not want these two to be eclipsed with each other. Now, we don't even want the ethyl to be eclipsed with the methyl, because there is a hydrogen here. So for this to be, and we have two hydrogens in the front, so we want this group to be eclipsed with the smallest thing on the back, which is this hydrogen right there. So I will, like my solutions, I will draw this up, and I want this hydrogen in the back to be eclipsed with it, okay? And then it doesn't matter how you fill in the rest. So on the back we have, let me draw it like my solutions. I have the iodine right there, and then I have the H over here. And then on the front, I have two hydrogens I've yet to draw, so I have an H right here, and then I also have an H right here. But I want to stress that the most stable eclipse, so we have to be eclipsed, which is not great energy-wise, but we want the best case scenario when we are eclipsed, and that's when the front group, the biggest front group, is eclipsed with the smallest back group, and you minimize all of those, situations. So I hope that makes sense, that the biggest thing we have, which isn't huge, is this ethyl group. So we pair it up with a hydrogen, and we make sure that the biggest thing in the back is paired up with the smallest thing in the front, which is also a hydrogen. Okay, so let me erase this quickly, and we need to do the last one of this problem. So to round out problem 2, we are tasked with drawing all of the staggered conformations of this structure that's given. So what we will do is just get your first structure, and then we can just fix either the front or the back, and then we just rotate and get all of our staggered conformations. So in the front, doesn't matter how you start, but let's start with the staggered conformation. So in the front, I have a chlorine, I have an isopropyl, and a hydrogen that is implied. And here, I'll make sure this is the front, this is the back, and in the back we have an ethyl and a methyl, so we can go ahead and do this, I'll even draw CH3, and we can fill it out with an H. So this is one staggered conformation. So what I'll do is I'll draw a dotted line, and just keep one fixed and rotate the other. So I'll just keep what I do in my solutions. I kept the front fixed. And just to be consistent, what I did was fine. I just want to make sure I'm consistent with the solutions I have provided on jOeCHEM, which are right here. So I had this right here. It doesn't matter, like I said, just trying to be consistent with anyone that might be watching. So there we go. Okay, so let me go ahead and turn the back. So all we're going to do is, okay, that's fine. Yeah, sorry. I'm going to turn the back just kind of a crank. So go ahead and redraw your front. Don't change anything in your front, or else you're going to maybe end up with a duplicate. So then I'm just going to have the methyl down here, the ethyl up here. All I'm doing is cranking this, so this ends up here, this ends up there, and this ends up here. And then my hydrogen is here. And then one more time, give it another crank. Again, if you're taking a test, make sure you crank and scare the person next to you. So again, keep the front, lock the front. You don't have to lock the front, but lock one, the front or the back. And then CH3 will be up here. Ethyl goes here, hydrogen goes down. And if you were to crank it one more time, you would see we'd end up with the CH, we'd end up with this structure right here. Okay, that's problem 3. Now we have 2 more. The last one's super teeny tiny alkane properties boiling point. The next one is probably maybe the more interesting one. We're going to do a whole conformational energy diagram with a Newman projection. So let's do it. Okay, gang, so in my opinion, 3 is kind of the star of this worksheet. So we're going to do the whole gambit. We're doing a full energy diagram of all the different Newman projection conformations of this structure from, the first Newman projection we draw to 360 degrees, and chopping it up into 60-degree increments, 60-degree turns, and ranking all of those different conformations relative to one another in terms of energy. So we can actually see, some energy, peaks and valleys and things like that. So this is the structure we are given right here. I'm going to go ahead and make this my front carbon. I'll make this my back carbon. And again, I have my trusty solution right here to make sure I'm actually doing exactly what I have posted on jOeCHEM as a solution. So and again, typically when you get this type of problem, to make sure your energy profile is exactly the same as everyone else's, if this is on a test, you will get, the same starting place. Of course, here, I didn't do that, probably should have done that, sorry. So, to start off, the Newman projection we are working with, remember, always home base, your front and back. The dot's the front, the circle is the back. We have the isopropyl group going up like this at 0. When I'm calling 0 degrees, have the methyl down right, we have an H down left. I'm going to start off with the bromine down there, H right here, the ethyl right there. So maybe you're thinking this is the anti-structure, and you're right. So when we turn 60 degrees, we go from staggered to eclipsed, and then when we do 60 more, we go from eclipsed to staggered. So it's always, every other, you're going to get the opposite. So when we rotate 60 degrees, let's make sure we do this clockwise, CW. So when we rotate 60 degrees, you're just going to have this bromine eclipsed with this hydrogen, this ethyl eclipsed with isopropyl eclipsed with the hydrogen. So we are going to have bromine, H, we're going to have isopropyl and ethyl. Let me just make sure this is darkened. and then we will have methyl. I'm going to keep the front locked. I'm going to rotate the back. So we have, this is eclipsed. So now let's do it 60 more degrees. So we were eclipsed, now we'll be staggered again. So keep the front the same. So really, you're not even touching the front, you're just touching the back. So now we have bromine here. Then we have, whoops, had a brain glitch. There we go. So let's do it 60 more degrees. So you can see this is very process oriented, just keeping a rhythm, making sure you don't make any mistakes from one to the next. So we're eclipsed. Sorry, that's a bad bromine, and then we have this right here. So I hope you're thinking, I hope you're grimacing a little bit, because this is maybe, possibly our worst structure. So 60 more degrees. Whoa. Keep the front the same. CH3, H. So now we'll be staggered, staggered, staggered. And if you're wondering why this is our last one, 360 is going to be the same as 0, so they are the same. So here I'll also put 360 up here. But last but not least, we will have our isopropyl going up, H going down left, methyl going down right. We have the bromine eclipsed here. We have the H eclipsed up here. We have the ethyl eclipsed here. Let me just double check that I didn't make any mistakes and I ended up in the exact same place on my solutions. Yes, I did. Okay, cool. So now we need to actually compare these and get to our energy diagram. So what I think helps the most is identifying your peak, your global peak and your global valley, meaning find your anti and find your worst eclipsed, right? So I think it's safe to say at 0 degrees, our isopropyl and our bromine, which are the two biggest groups we have, they are anti to one another. There's no other scenario where that's the case, where we are staggered and they are both, remember, opposite from one another. So at 0 and 360, I'm going to put my lowest tick. Now remember, because we are energy diagram pros, I'm going to try and keep them on the same level. If they're not at the same level, that's just me sucking at being level. But remember, going up in energy means more unstable. Lower means we are lower energy and more stable. So 0 is our best. This is anti. Okay? So our worst interaction, let's see if we have our isopropyl and bromine eclipse on one another. Sure enough, at 180, that is the case. So at 180, I'm going to make this is our ceiling. Nothing should be higher than this. This needs to be the highest in this energy diagram. Of course, no numbers, just relative to one another, okay? So let's see if we can maybe find, let's find the, let's work our way down from the worst. And then find ourselves getting, a tick for every location. So let's look at 60 and 180, or sorry, not 180, 60 and 300. So this is a bit close, bit of a hard part of this example. I wish I made it a bit more clear cut. However, I think it's okay in the overall example. So we really need to look at the fact that we have, bromine and hydrogen eclipsed, methyl and hydrogen eclipsed, and this branched isopropyl and this ethyl group right there. And then, 300 degrees, we have bromine with a very tiny methyl group, the ethyl with a hydrogen, and then the isopropyl with a hydrogen. So I have to, it's either going to be, admittedly, gang, I'm sorry about this, it'd either be 60, a little higher energy, 300, just below it, or vice versa. And in the solution, I said that the branched isopropyl, being eclipsed with the ethyl group is a little bit worse, higher energy than this right here. So if we have the 60 right here, then the 300 will be just below it. So don't get caught up too much about that. I think the overall process, you're still going through it, is totally fine. Now we just need to fill in 120 and 240. So if you look here, we kind of need to see if one is better than the other. And if you take a look here, we really need to see bromine. Bromine is goes to a methyl group and an isopropyl group, but over here, bromine goes to an isopropyl group and hydrogen. So we have to kind of decide, is bromine being goes to isopropyl and methyl worse than ethyl being goes to methyl and isopropyl? And I think definitely yes, because we kind of have the two largest groups in the front, you know, being goes to the biggest group on the back versus the two biggest groups in the front just being, and we have this interaction as well, versus just this right here. So I'm saying 240 is higher energy than 120. So 120 is above 0 and 360. And then above that is 240, so right here. Okay? So now we get to do the fun part, which is ride the wave, connect the dots as far as how this energy diagram looks when these single bonds are rotating. Okay? It's not pretty, but it does the job. So you won't get such a iffy example when you're, when you have a test or anything like that. It'll be very clear cut, so I apologize for the 16-300 being a little ambiguous, but I'm sure between this example and the one we did in the video, you all have this down. So one more tiny example and then we're done with the Newman projection state of mind worksheet. Okay gang, to round out this worksheet, we're just going to rank the following alkanes from 1 to 3, 1 being the lowest boiling point, 3 being the highest boiling point. And remember, boiling point goes by molecular weight, and if you have a tie in molecular weight, the boiling point is higher with the structure that is less branched. More branching means lower boiling point. So if we take a look right here, obviously we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So clearly the structure with 5 carbons, lowest boiling point, that gets a 1. And since we have a tie here, 6 carbons, we have hexane and we have this structure right here. This is much more branched, second highest boiling point, and hexane takes home the boiling point crown with number 3. Gang, thank you for sticking through me in this Newman projection worksheet. If you're watching this video, that means you've thrown me some money and you've supported jOeCHEM. I so unbelievably appreciate that. Thank you for using jOeCHEM as an outlet to learn organic chemistry. I'm so happy and humbled to be a part of your journey through OCHEM. And I hope to be there to the very end. And if anything, I hope to see you all in the next video.